I'd like to introduce Leo St. Amour. Leo is a master's student at Northeastern University and a military fellow at MIT Lincoln Laboratory. He graduated from the United States Military Academy in May of 2015, where he worked on TLS library with enhanced usability and security. In addition to his work on the TLS and Accumulo, he is currently working on binary analysis with a focus on discovering and hardening security properties. Again, that's probably what you're about to hear about. So, Leo.
All right, thank you so much. My name is Leo St. Amour. I'm here with MIT Lincoln Laboratory, and today I would like to talk to you about authenticated data structures and how we can use them to verify the integrity of Accumulo query results. So first, I'd like to begin by discussing the threat model that we're operating within. And in order to do that, we need to talk about a couple of different classes of threats that Accumulo systems face. First, Accumulo can face malicious clients. We do not want clients to make any sorts of unauthorized queries or to learn information about either the data that is stored in Accumulo or about the queries that other clients are making. The second class of threats are external attacks, and these deal with malware or attempted hacks or compromising some of the systems. And the third class of threat is dealing with a malicious cloud server or an administrator. We don't want the administrators to learn the contents of the data or the queries that are being made. We do not want the administrators to be able to modify, forge, delete, or change the data in any way. And we don't want them to be able to misattribute the data to honest clients. So the focus of today's talk is going to be on this third class of threat, the malicious server or administrator. The first class of threats is out of scope, even though there is a lot of interesting research being done on making sure that users are only able to make authorized queries. The second class of threats is also out of scope because there are existing methods for dealing with malware or other types of compromises, including antivirus, firewalls, or intrusion detection systems. So again, we're going to focus on this third class of threats, which deals with a malicious server or administrator. Now, there are a number of different administrators that could be involved in an Accumulo setup. If we want to make sure that the Hadoop administrator doesn't learn the contents of the files that are being stored on the Hadoop file system, we can simply use data at rest encryption to make sure that in the event that this particular administrator is malicious, that they don't learn any of the data. If we're worried that the network administrator might be malicious and be sniffing the traffic going across the network in between the clients and the server, we can use data in motion encryption, such as the TLS protocol, in order to protect that data. However, when we focus in on this third type of administrator, the Accumulo administrator itself, there are actually no safeguards being provided to prevent this administrator from learning the contents of the data on Accumulo or modifying or changing it in some way. So our goal is to use cryptography in order to protect Accumulo against malicious insiders. We provide a couple of mechanisms for doing that. The first set of mechanisms, which my colleague Scott just spoke about, are using encryption and cryptography to protect the confidentiality of the data, which means making sure that the actual content of the data isn't accessed by people who are not allowed to access it. I'm going to be talking about work that deals with guaranteeing the integrity of the data, which means making sure that the data hasn't been tampered with or modified in some sort of way. The focus of this talk is primarily going to be verifiable query results. However, I'd like to start by talking briefly about some of the work we have done using digital signatures to guarantee the integrity of data in Accumulo. So last year we spoke at the Accumulo Summit about our work with verifying query results using digital signatures, and it's very similar to the process of using signatures with emails. So the data source will sign the data prior to writing it out to Accumulo, and whenever a client queries the data, they're able to use the data source's public key to verify that the data they're receiving is correct. So we're going to go through 3 examples that demonstrate the security properties of these digital signatures. First, there's the event that Accumulo operates the way we all expect it to. So we have a situation here where we have one client who's going to query across all the records within an Accumulo database, and these 2 records that are in the database have been signed. So the client receives the data and can use the public key to check, yes, this is the data I'm expecting to get, and it is correct. If we move into a situation where we have a malicious administrator who is able to in some way either insert some sort of faulty record and can't use the appropriate signature to sign it, or modifies the data in some way, when these records are returned to the client, it will be able to use the keys to verify whether or not they're correct, and the last one will let them know, no, the data you have received is not correct. There is some sort of issue with the integrity of it. But an issue arises if Accumulo decides to not return a complete set of correct results. So if the client queries the entire data set, but Accumulo decides only to send one of these two records, using digital signatures, the client will verify that this is a correct response to the query I've just made. However, it's obviously not the correct response. The data is incomplete, and digital signatures are not able to detect maliciously omitted query results. So how do we approach this problem? Our solution is to use authenticated data structures. And what an authenticated data structure is a data structure that contains a large set of data and a digest that is dependent upon every element within that data set. And this digest allows us to check whether or not results have been omitted. In addition to this improved security, authenticated data structures would also give us a performance improvement. So this graph demonstrates our micro-benchmarking of our authenticated data structure versus the signatures implementation. It shows the running times for 3 different operations: the creation of the data set, querying for a single element, or conducting a range query over 2,000 elements. And you should note that the scale of time is logarithmic, so there's a drastic improvement from using authenticated data structures over digital signatures. So we want to be able to gain both the security improvement as well as an improvement in performance. And that's what we've been doing. So these are the contributions that we've made that I'd like to discuss today. The first one is that we've developed a scheme for embedding an authenticated data structure in an Accumulo instance. And this will allow for clients to be able to verify that the results are not only correct but also complete, which is an aspect that was missing from our previous work. We've prototyped this concept using a Python client-side library, and it's in the process of being open sourced. And as Scott mentioned in his talk, if anyone out there is really eager to learn how this concept works, they should look at this Python library as soon as it's released. But the primary contribution is a Java library, and we are trying to leverage the power of Accumulo iterators in order to improve efficiency over our current prototype, as well as design a drop-in API that's very easy for developers to port their existing applications over, as well as provide them with an API that they're familiar with to use for future applications. And this Java library should be coming in the first quarter of the next calendar year. Again, our team is very interested in community involvement. If anyone is interested in learning more information about the products that we're making, finding out about dates when these codes will be open sourced, or is interested in testing our implementations once they've been open sourced, please feel free to contact us, paste-contact@ll.mit.edu. Now, if you haven't written this email address down yet, don't worry, I'll display it again at the end of the presentation. So we've decided to use authenticated data structures in order to add this completeness check to our integrity verification. And I'm going to take a few minutes now to discuss how authenticated data structures fit into the overall Accumulo system. I'm going to talk about the specific data structure that we decided to use and give some examples about how that can be used to construct the proofs that allow the client to verify the completeness and correctness of their queries. So we have a typical Accumulo setup with a data source, some sort of querying client, and an Accumulo server. We want to be able to allow provably correct and complete query results. In this context, correctness is defined by the data source, who is supposedly a trusted data owner. The data source will insert their data into the Accumulo, and at the same time construct an authenticated data structure that contains all of the exact same data. At the root of this data structure is a digest, which is a small value that will represent the entire data set. The data source will sign and publish this digest for the querying clients to access. The authenticated data structure is then written out to Accumulo. Whenever a client needs to make a query, in addition to the results that they'd get back from Accumulo by itself, they will also receive a verification object. And a verification object is essentially a proof. It contains all the data necessary for the client to reconstruct the authenticated data structures digest in order to recompute it. When it receives this verification object, the client will recompute the digest, which is supposed to represent the data they've just received in response from Accumulo. And if they can compare that to the publicly available digest and it matches, the query results are both complete and correct. However, if we're operating in an environment with a malicious administrator and the verification object has been altered in some sort of way, any data has been modified, forged, or deleted, when the client receives this verification object, the recalculated digest will not match the publicly available one, and that client will know that their results are either incorrect or incomplete in some sort of way. The authenticated data structure that we decided to use is called a skip list. And a skip list is a expected balanced tree-like data structure that uses randomness to guarantee that in all but the rarest of cases, lookup, insert, and verify operations will occur in logarithmic time. So the reason that we chose to use skip lists is because they're highly efficient, and because they have efficient runtimes for specifically the insert operations, they are ideal for dynamic data sets and for applications such as Accumulo with a high ingest rate. Our decision to use skip list was kind of validated when looking through the Accumulo internals, and we found that the skip list is actually one of the potential data structures used for the back end of the tablet servers. So in order to discuss some of the properties of skip lists, I'm going to present an example of how to construct one, as well as an example of how we can look up some sort of element within the skip list, which is akin to a point query. So we're going to begin by constructing a skip list that contains all of the even numbers 2 through 12 inclusive. So first we have to establish boundary elements. I'd like to take a moment to note that a skip list is essentially a series of linked lists that are going to be stacked on top of each other. And each layer has at least as many elements as the layer below it. So as we insert our elements, we'll start by inserting 2. After each insertion, a coin is flipped, and this is where the randomness comes in. If the coin flips heads, we add that element to the next layer above it. However, if we flip the coin and it's tails, we are done with that particular element and we move on to the next one. So we move on to 4. We flip our coin, it comes up tails, now we would move on to 6, and we would repeat this process for the rest of the elements in our data set. What makes skip lists useful in addition to their quick lookups is the fact that the insertion time will be logarithmic, and it's also it's independent of the order of what the data, how the data comes into Accumulo. So that makes it ideal for dynamic data sets and allows it for quick, efficient updates. So let's look at how we would query through data in a skip list. Let's say we're looking to see whether or not the element 12 is in our list, in our data set. Functionally, it's very similar to a binary search tree. At each node, you will compare the value that you're looking for to its neighbor. In this particular situation, 12 is less than infinity, so we traverse down the tree. 12 is not less than 8, so we traverse to the right. We continue this process until eventually we reach the bottom of the tree, and once we've reached the bottom, we can verify that 12 is in the data set. That's the node that we're currently at, so 12 is a member of our data set. And by pruning out these edges, it allows us to have these authenticated operations that run logarithmic because, again, it's very similar to a binary search tree. So these data structures are essentially useless unless we have some way of constructing the digest that I was talking about before. And I'm not going to go into the exact algorithmic details of how these nodes are labeled, but the important thing to note is that every node, their label, is dependent upon all of the subsequent nodes. So in this little example, we're going to start by assigning some label to the 6th node. Its neighbor, the 4, has a label that is the hash value of its value as well as the value of its neighbor. The 2 node has a hash that depends on its value as well as the hash of its neighbor. The 6 depends upon the label of its downward neighbor, and this 2 depends on the hash of its downward neighbor and the hash of its rightward neighbor. So what's important to realize here is that the hash that's in the upper left node, which for the sake of this example is similar to the root of the whole skip list, is dependent upon pieces of data or information from every other node within the skip list. So we use this process and we calculate the digest at the root of our authenticated skip list. And this allows us to conduct range queries. So let's say we want to query over the range 1 through 5. Obviously the answer is going to be 2 and 4, and that's what's going to be returned by Accumulo. But what we want to do now is construct a verification object that contains all the nodes we need in order to recalculate the digest at the root of the tree. So from this point on, as I step through this example, all of the nodes that are going to be highlighted in red are components of the verification object, and all of the nodes that will be highlighted in blue are nodes that we're able to calculate ourselves, based upon previously given information or what we've already seen in the verification object. So one of the limitations of our approach is that we can't actually verify the completeness of a query without returning the boundary elements of the range query. So the negative infinity and the 6 that are adjacent to the results will be returned as part of our verification object. Using existing information, we're able to calculate what the labels would be at these 2 nodes. However, the next node up the skip list, we cannot calculate unless we know what the value at the 6th node is. We continue this process and traverse back up the tree until we end up at the root. Once we've recalculated this digest, as I mentioned before, we can compare it to the publicly available digest that was put out by the data source, and it'll let us know if the results are complete and correct. So staying on this example, in the event that that 4 were maliciously modified to be a 3, based upon the primitives of hash functions, every subsequent node traversing up the tree would have an incorrect hash value, so the root would also be incorrect. So we've been able to successfully embed these data structures within Accumulo, which allows our clients to, in addition to their queries, get back information about the verification object to construct these proofs. So I'd like to take a few minutes now to discuss our scheme for embedding the authenticated data structures within Accumulo, and then I will discuss how we use that within our Java library to make it available for developers to use. So here we have an arbitrary component of some skip list. We're going to focus our attentions on this middle node that's highlighted in green, which contains the value 8. To make this demonstration a little bit easier to follow, we're going to give them arbitrary node names. So what would this skip list look like, or this component of the skip list look like in an Accumulo table? The entire authenticated data structure is actually stored in a single row, and every node within the data structure is stored in a single column. In the value field, you'll find a JSON object that contains metadata associated with each node. So we'll look at an example node, node 3. Node 3 contains, the value for node 3 contains all the information we would need to reconstruct this node once it's been extracted from the Accumulo table. It contains the element of 8, it contains the label that I just discussed, but base 64 encoded, and as well as information about what all of its neighboring nodes are, its downward neighbor, its rightward neighbor, and its information about its parent. Using this metadata, we've developed a method for pulling all the information out of the table and reconstructing the object that we want, so that way we can use it to make range queries and create our verification objects. As I mentioned, we've prototyped our design, and it's currently implemented as a client-side Python library. But at the moment, the client is responsible, or the client-side software is responsible for computing this verification object. And the way that this looks is the client will query Accumulo to get back the results that they expected. And then from there, they are responsible for querying Accumulo in order to find the node of their verification object, as well as that node's metadata, and then move on to the next node and look for its metadata. And it's this very iterative process that results in a high amount of communication overhead. This is a pretty big issue because one of the appeals of using the authenticated data structures is that they actually provide us with a drastic speed up and improvement in performance. So in order to address this problem, we decided that we need to shift this verification object construction away from the client and onto the server. So similar to the first talk we heard this morning, we also tried to leverage the power of Accumulo iterators. Not only would they allow us to perform server-side computation, but they allow us to implement our library without requiring any sorts of modification to Accumulo internals, which would make it much more portable. So the way this would look is the client would make their query to Accumulo and retrieve their results. Then Accumulo itself, using the iterators, will compute the verification object and then return that verification object for the client to use to actually verify their results. And this obviously reduces the vast amount of communication overhead we saw in the previous implementation. So moving forward now, I'd like to discuss what our API is going to look like, as well as some of the details about how we've implemented it. Here we have an example Accumulo client taken right out of the Accumulo documentation. So what this code does is it creates a connection, it populates some data into a mutation, it writes that mutation to a table, and then scans all the elements in that table. So we wanted to make it really easy for existing applications to have this, to use our approach with a drop-in sort of replacement API that would make it very easy for them to port over their existing applications, as well as be something that they're familiar with, so that way their workflow isn't too interrupted in order to gain these security benefits. So the way that looks is we simply replace two lines. So what this code does is it creates a connection, it populates a mutation, writes the mutation, and then scans the table. So it's essentially the exact same code, with the exception of using two custom classes, the writer class and the scanner class. I'd like to take some time now to talk about the scanner class. We wanted it to be functionally exactly the same as the existing batch scanner. And the way we approach that is by using our custom scanner to wrap to other scanner objects. One of those scanner objects, the first one, which I've called this.scanner, will be the actual table that the user is trying to query and get results from. The user will also want to scan the metadata table, which I've called the metascanner. We acknowledge that there are many different ways we can envision storing these authenticated data structures, and we want to leave that up to the actual server administrator, whether or not the authenticated data structure is stored in its own separate table or stored as a specific row amongst the data that you're trying to scan. Either way, we've tried to make it flexible, and this implementation allows for that. Before I move on, I got to make sure that I clarify some of the terminology I'm about to use, because the fact that Accumulo iterators and Java iterators are slightly different but still have the same terminology, I want to make it clear what I'm using. When I say iterator, I'm referring to an iterable Java object. When I say Accumulo iterator, I'm referring to the classes that are used in order to make the tablet servers do some sort of computation on scanning or compaction. So when we go over when we instantiate the iterable that's associated with our custom scanner, what it does is it applies a custom Accumulo iterator to the metadata scanner. And once that table is actually scanned, the only result in it will be the proof. After that proof has been constructed and returned to the verify scanner iterator, or the Java iterable associated with our custom scanner, we will verify the proof and then track whether or not it has been verified, and that will come into play in a couple of minutes. The custom iterator, the Accumulo iterator that we've chosen to implement, extends the existing row encoding iterator. We have come up with a scheme that places the entire authenticated data structure in a single row. And what the row encoding iterator allows us to do is take advantage of this row encoder method, which gives us a list of keys and a list of values that contain all of the columns and all of the values that are within a given row. And it allows us to do calculations on this aggregate data associated with one row. So what we do is we use our method for reconstructing the skip list using these keys and values. We're then able to call the range query method on the skip list and return that proof to the user. And as I mentioned before, we track whether or not that proof has been verified. And if it has been verified, the verify scanner class will only return results once it's been verified. If it's not, the user will not get any results in response to their query. So I'd like to conclude this talk by discussing some of the limitations of our approach, as well as some future work as how we attempt to approach those issues. As I mentioned before, our current implementation returns the boundary elements associated with a range query, and this could potentially lead to unnecessary data leakage. Additionally, the verification objects do not actually support visibility fields. So a proof may contain data that the client is not actually authorized to see, and obviously this could lead to some potential issues with confidentiality or access control. So what we want to do is develop a method for verifying the completeness without actually leaking these boundaries, and develop something called a visibility-aware authenticated data structure that takes into account these situations where a user could be querying across a range that contains elements that they are both authorized to see as well as elements that they are not authorized to see, and find a way to still keep that data hidden while verifying the completeness. So again, today we've talked about the scheme that we've developed for embedding authenticated data structures within Accumulo, which allows for us to verify that these results are correct and complete. This has already been implemented as a proof of concept library written in Python that will be coming very soon. It's in the process of being open sourced. And we're implementing a Java library that allows us to leverage iterators to improve the efficiency of our approach, as well as create a drop-in API that is familiar to developers, and that should be coming within the first quarter of the next calendar year. Again, we would really appreciate community input on these ideas, and we would like people to reach out to us to ask questions and let us know if anyone is willing to test our implementations once they have been open sourced. I thank you for your time, and I'd be open to any questions. Yes, sir.
Verification client side, does this apply a slightly different threat model?
So the question was, if the verification is client-side, does that address a different threat model? No, I don't think it addresses a different threat model. We are still worried about the server providing us with forged or modified or incorrect data. And all of the metadata associated with the skip list is also stored in Accumulo. So the client is a trusted user in this particular case. So they are getting all the data back from Accumulo, and our threat is then focused on making sure that that data that they're receiving back has not been tampered with in any way. Yes, sir.
I have three questions.
Okay.
The first is, do you have any more realistic example of the authenticated data structure search, which you explain using numbers?
Okay. Okay. One moment. So the question was, are there any more realistic examples of searching through an authenticated data structure than simply using numbers? So the data that's stored in Accumulo is ordered in some way, and it's arbitrary what kind of data is in there. It doesn't have to be numbers. This could be, an example we talked about earlier was medical records. So say we're searching for a node which represents the medical record or a diagnosis for some patient. So instead of being just an integer like a 10, the node would consist of an object that is meant to be an Accumulo entry node, and it would contain attributes that represent the row, the column family, column qualifier, the timestamp, and the value. So each of these nodes would actually be akin to an entry in Accumulo. Does that answer your question? Okay. If you want further detail, please feel free to talk to me after.
Second question is,
Yes.
do you have any plans of, actually more of the legal lab in general that Jeremiah was explaining about the enforcement of visibility views?
Yes.
Like having a solution which encompasses both the technologies rather than just one?
Okay, so the question was, Do we have any plans to encompass both the technologies that were discussed in the two MIT Lincoln Laboratory talks, both the integrity checks with the authenticated data structures as well as the work on access control that Scott just spoke about? As far as I understand, these are not mutually exclusive technologies, and we are looking into ways to combine both of these different scanners that we've talked about. In theory, they could probably be combined, but we haven't actually made any steps towards doing that yet.
Because the way I see that you're using specific scanners and specific
Right.
right patch, like implementation of patch drivers.
Right.
Utilize it.
So we haven't gotten to that point yet. Ideally, we would want to gain all these security benefits that we've talked about simultaneously, as long as it doesn't have an impossible performance cost. But we haven't actually made those steps yet.
And the final question just to the Lincoln Lab, any thoughts of putting it to Scala rather than just Java?
I don't think we put any thought into that, as far as I'm aware, but that is something I guess we could discuss with you afterwards if you would like to explain the use cases or the extensibility of that. Any other questions? Yes, sir.
So you propose that you're going to compare the public sector digest to the return
Yes.
verification. Where does that get created and stored? What prevents someone from forging both that?
The public hash?
Right.
So the public hash will, one, it will be signed by the data owner, which makes sure that it's authentic. So that prevents, that answers that second.
Responsibility of the owner.
That is the responsibility of the owner to sign that data before publishing it. And in terms of where it's stored, that's left up to the discretion of who's ever setting up the system.
You should not have if that also gets stored.
Right, it wouldn't make sense if we're worried about a malicious server administrator to put it on the exact same server, similar to what Scott was talking about in the previous talk, where we wouldn't want our key management system to be in the same potentially malicious server. Yeah. All right, thank you for your time.
I have two quick announcements. First is the Accumulo Hackathon is at 6 o'clock tonight, and if you have not already registered but still would like to go, just let me know or show me your hand. They're ordering pizza, and they want to make sure they have enough food for everyone.